Welcome back everyone to part 2 of the chapter 6 video on energy. So in this part, we are going to look at work done and power. So what we are going to focus on are the two formulas. Work done equals to force times distance and power equals to energy over time. So the definition of work done, okay, is the product of the force and the distance moved by the object. So this works for a constant force, which is the only context that we are going to consider in the syllabus. Okay, so the formula would just simply be the constant force in newtons multiplied by the distance moved in the direction of force in meters. Okay, it's very important that you remember that these two things must be in the same direction. If they're not in the same direction, okay, work is not going to be done. For our syllabus, we're only ever going to consider the force and the distance moved either being in the same direction or being in perpendicular directions. So, for example, if you push something upwards and it moves to the side, no work is being done because something else, there's some other force causing the object to move sideways. Now, a question that you will see in your notes is why are the units for work done the same as that of energy, right? How come work done is in joules as well? Aren't these two different concepts? Okay, very simply put, remember that just now, in the previous video, what we had was that energy was in different stores. And the analogy that I used was that these different stores are like different bank accounts, and the energy is like the money that is contained within these bank accounts. Now, work is just like the transfer, of energy from one account to another account. So, of course, it has to be in the same units. When you transfer money from one account to another account, you are doing so, in the same units. Let's say, for example, in dollars, right? So, from your savings account to your daily expenditure, if you're paying someone money, you're going to be doing so in the same units. That is why, work done is going to have the same units as energy stores. So for power, it is defined by the work done or the energy transferred per unit time. The SI unit for power is the watts, represented by capital W. Now this might be a little bit confusing because W, is used to represent quite a number of things. In the previous chapters we had W to represent weight. In this chapter we had W to represent work done, and now W as a unit, the watts is the SI unit for power. So please be very very careful. Make sure that you know the context when you write W. And if you're worried that you make this confusion, you don't have to shorten it. You can always write down watts, weight, work. This will help you prevent any confusion, if you are worried that your concepts are still a little bit shaky, you're a bit unfamiliar because it's new, and that's why you want to write the names of each of these units or the things that they represent in full when it comes to the formulas. So an example here for power is electric kettle. Let's say it is 1,500 watts. So what it means is that every second 1,500 joules is being transferred from the power source to the internal store of the heating element and the water. So 1,500 joules every second is being transferred, in this case via electricity. So looking at our worked examples, so worked example 7, we've got a box placed on a smooth floor and 8 newtons acting horizontally on it. The box moves 3 meters in the direction of the force, and we want to calculate the work done by the force and the energy increase in the kinetic store of the box. So the work done will simply be, using our formula, W equals to F times S, force times the distance traveled in the direction of the force, 8 newtons times 3 meters, 24 joules. Now for part 2, kinetic store, you will notice that it says that the box is placed on a smooth floor. So because the floor is smooth, What that means is there is no transfer of energy to other stores because friction doesn't exist over here to transfer some of that kinetic store into internal store or to transfer energy outside the system in the form of sound. So just from using the conservation of energy, the work done on a box gives us the increase in the energy of the kinetic store. So again, 24 joules is the answer here. So just like, okay, the analogy of transferring money from one account to another account. If you pay someone $24, okay, it means your account loses $24 and they should gain $24. So worked example 8, we got a weightlifter lifting 100 kilograms, 1.8 meters off the ground over 1.2 seconds. Calculate the power she generates to do so. So our first way of doing it is power equals to the energy over time. And in this case, when you're lifting the weight, what you're going to have is the energy in the gravitational potential store. So we use our formula in our previous part of this chapter, mgh. Okay, substitute our values in there, 100 kilograms, 10 newtons per kg, and 1.8 meters. And then we divide straight away by the time that she takes. So this gives us our answer of 1500 watts. Now, the other approach instead is to consider the work that she does, because we also know that power is work done over time. So this different approach, okay, you will see that it's the force times the distance traveled. And of course, in order to lift something, you must act against the weight. So what you're doing here is you're using the weight. So W equals to mg. Okay, I've deliberately omitted W here because I didn't want to confuse you with too many W's. And we get, again, you will realize the same numbers. And our work done is 1800 joules. After that, in order to find the power, we take the work over time. Okay, so we divide that by 1.2 seconds and we get the same answer of 1500 watts. So we realize that both methods work, okay? Whichever method you use, whichever method you prefer, okay, would really be up to you. Both will give you the same answer because actually both of them use exactly the same numbers. It's just whether you are doing it all in one step, which you can do if you're more comfortable with it, or you do it in multiple steps because you want to make sure that on each step you are explaining it very clearly. Part B, we have electric motor in a washing machine with a power output of 1 kilowatt. Calculate the work done in half an hour. So we use our formula, okay? Power equals to work over time, do a little bit of algebra, and we get that work equals to the power multiplied by the duration. Now, 1 kilowatt is 1000 watts because as you recall, back in chapter 1, okay, our prefixes, kilo is 1000, and half an hour is 30 minutes times 60 seconds because the SI unit for time is seconds. So when you multiply all this together, you will get 1.8 million joules. And I've given you two other representations, which is 1.8 megajoules. Okay, remembering that mega is for million, or 1.8 times 10 to the power of 6 joules, which is the standard form where you take a number between 1 and 10 times 10 to the power of a whole number. Okay, so you see that this second part of the chapter actually is much more straightforward because we actually do not need that much more formulas, and the bulk of this chapter was understanding the ideas of energy, energy stores, and the transfer of energy. Okay, so as always, if you need to repeat, okay, please pause this video. You can watch it again, different sections, or slow it down.